So I'll talk about some things that I've been working on for a while, but I'll give you the latest reference just in case you want to see. So the title of the talk is Twisting the Superstring, and I should start by giving a little bit motivation about why people want to understand the superstring better. So again, I'm not so accustomed to giving a talk to mathematicians, so maybe there are some things that will be obvious to you that are not obvious to me and vice versa. But please ask questions so I have an idea of what's going to and what's not. Okay? So when people say superstring, they mean a supersymmetric version of the ordinary string. So the ordinary string is described by a coordinate, which is a bosonic coordinate, which is vector in space-time. And one usually uses the parameters tau and sigma to describe the time direction and the internal direction of the string. So this would describe a closed string. You can also have an open string where sigma just has endpoints. So the interesting thing is that when you try to quantize this theory, so it's a two-dimensional theory because it depends on tau and sigma, you find that it describes a space-time theory containing gravity. So the bosonic string theory can be written, well, normally one uses complex coordinates. So one does a conformal transformation of the complex plane. So this becomes dz and dz bar. And for the bosonic string, we have a theory of this type. So this is the two-dimensional action. And the idea is that you get physics out of it. By defining some kind of two-dimensional correlation function. So this is supposed to be a path integral over all the x's. So for bosonic string theory, you have 26 of these. And then the idea is you're supposed to integrate over all surfaces which connect incoming and outgoing strings. So this is supposed to be incoming strings, this is outgoing strings. And this would be a tree amplitude because there are no loops. But of course, you could also include surfaces of higher genus. And you're supposed to sum over all the genus with, also there's a coupling constant which tells you essentially, sorry, let's go again. So G is the genus of the surface, so this would be the thing that tells you how strong the coupling of the string theory is. Okay, there's one more ingredient you need, which is operators which tell you what the external states are. So I already mentioned one possible external state is the graviton. So for the graviton, you would consider adding, I'm writing it this way. You consider this type of operator. So this is supposed to be at least a graviton where GMN is very small. So if you add this to the action, you would get something that looks like the string. Maybe I should call it H because it's the part of the metric which is different from the Minkowski metric. So this is supposed to be thought of as a perturbation of flat space-time, and this describes the scattering of gravitons. So if you compute this kind of amplitude, which I could also write in terms of so if I think of this as S0 and this is the interaction, I could think of doing the same computation by integrating over the original flat space action with these insertions of vertex operators. So this describes a scattering amplitude computation of n gravitons. Okay? So this was studied in the 70s, and people quickly understood that it describes at the classical level, it describes general relativity, but it includes higher energy corrections. And in fact, the idea is that this is a quantum mechanical theory. It turns out quantum mechanical theory of general relativity is hard to invent, but this actually almost works. It almost works in the sense that at least you can compute quantum mechanical corrections to general relativity, but it turns out they diverge. So this theory, which is bosonic string theory, has essentially, well, similar problems to just quantization of general relativity. Of course, it has extra states. It's not just gravitons. But it turns out to have problems. So the way these problems were solved was by a new theory, which was called the superstring, in which, in addition to bosonic coordinates, you also have fermionic coordinates. So bosonic coordinates means commuting classically, and by fermionic, I mean that classically they're anti-commuting. So the action is similar. Just for convenience, I'll only describe one type of psi. It turns out you could have psis which are holomorphic and psis which are anti-holomorphic, but let me just stick with the holomorphic one. Now, it turns out we can still describe gravitons, but it turns out this theory, in addition to having bosonic degrees of freedom, like the graviton, it also has fermionic degrees of freedom. So for example, in physics, the electron is a fermion, it's not a boson. Now, it turns out that when you have space-time bosons and space-time fermions, computing amplitudes is slightly more delicate because, so now you have to okay, so there are two ways to interpret it. So this can be interpreted as a two-dimensional Lagrangian, or two-dimensional action. So in that sense, this is a two-dimensional field theory. It turns out to be a conformal field theory because the action, well, I should have mentioned this. These vertex operators are supposed to be conformal primaries. So this is a two-dimensional conformal field theory. Now, you can also interpret it as, in this case, a 26-dimensional field theory, where these are the amplitudes. But I never wrote down a Lagrangian in 26 dimensions. So in that sense, it's more natural to understand as a two-dimensional field theory, which you can use to compute not the 26-dimensional Lagrangian, but the S matrix in 26 dimensions. So the S matrix in 26 dimensions just describes the amplitudes of 26-dimensional particles moving in 26 dimensions. But it doesn't come from a 26-dimensional field theory. Okay, so I don't know if that answered your question. Any other questions? Okay, so for the superstring, it turns out that, so for the bosonic string, in order to be conformally invariant at the quantum level, m had to be equal 26. So m goes to 0 to 25. For the superstring, in order to be conformally invariant at the quantum level in the two-dimensional sense, so this is just the usual super-Virasoro algebra, m has to go from 0 to 9. Okay, so it's just a simple quantum computation to show that this is conformally invariant if there are 10 x's and 10 psis. So in this case, one also has, so one can do something similar. Now, just to simplify the notation, I'm going to only, from this point on, I'll just restrict to the excitations which correspond not to the graviton, but to the gluon. So it's a vector in space-time. So, of course, I can use this to describe gravitons, but it turns out there's also a vertex operator to describe a gluon or a photon, which is a vector. And that would just couple to 1x. Now, it turns out that's relevant if you have the string with boundaries. So I'm not going to go into details about this, but just because I have, instead of having to talk about holomorphic and anti-holomorphic, in this vertex operator, I only have to talk about holomorphic. So I'll just restrict my attention from now to the gluons and its supersymmetric partner instead of the graviton, okay, just to simplify the notation. But everything I say about the gluon, which is this vector in space-time, generalizes in a straightforward way to the graviton. Okay. So it turns out for the superstring, instead of having conformal invariance, so conformal invariance is, of course, described by just a stress tensor. For the superstring, you have T, the usual Virasoro generator, which, of course, now has a contribution from the psi's. You also have a super Virasoro part, which is psi m d. So psi, just looking at the stress tensor, you can see that psi has spin 1/2, whereas x, of course, or dx has spin 1. Okay, so g has spin 3/2. Okay, now if you want to preserve this n equals 1 superconformal invariance, you have to add vertex operators, which is n equals 1 superconformal primaries. And the analog of this vertex operator for the superstring is now this operator. Okay, so it's spin 1/2, and this is going to be the field that describes the gluon. So we can compute, instead of computing graviton scattering amplitudes in 10 dimensions, now we're computing gluon scattering amplitudes in 10 dimensions, but using the same prescription here. Okay, so it's supposed to sum over all surfaces that connect external strings that are describing these gluons. Okay, but of course the gluons are bosonic particles. And as I already mentioned, the reason why we want to study the superstring is because it also describes fermionic particles like the electron. And it turns out it involves these bosonic and fermionic particles in a way which preserves a symmetry. And the symmetry is called space-time supersymmetry. So there's a space-time supersymmetry. These are space-time bosons. This is AM. But they're also space-time fermions. So let me call it psi. So if I call this the gluon, this is called the gluino. So this is a vector in space-time. That's why I had the index m. So m is 0 to 9. It turns out a space-time spinner in 10 dimensions, the minimal dimension is 16. So this space-time spinner has 16 components. And we want to describe both space-time bosons and space-time fermions, because if we can only describe the space-time bosons, we will never see the space-time supersymmetry, which is necessary in order to make this a consistent theory. Now, the vertex for the space-time fermions is much more complicated. So let me try to explain why it's more complicated. So psi, as I already mentioned, has spin 1/2 on the world sheet. Now what that means is that if I go around the circle here, because it's spin 1/2, it can either come back to itself or it can come back to itself with a minus sign. If it comes back with a plus sign, it's called Reimundo. If it comes back with a minus sign, it's called Neverschwarz. The reason is because these were the people who first described the superstring, and Reimundo turned out to consider psi with this periodic boundary condition and Neverschwarz with antiperiodic. Now these turn out to describe fermions, space-time fermions. So in this sector of the theory, when you quantize, you get space-time fermions. Whereas in this sector of the theory, when you quantize, you get space-time bosons. Now, it looks a little bit counterintuitive, but it turns out when you do a conformal transformation of this cylinder to the plane, it turns out that psi m of z, so if I'm using the conformal transformation where log z is equal to tau plus I sigma, it turns out if you take z around a circle around v, a z, so this is z, it turns out this comes back to itself with a minus sign in the Reimundo sector. and with a plus sign in Navier-Schwarz. So there's a change in sign just because of the square root cut, because it's spin 1/2. Now, in the Navier-Schwarz sector, it comes back with a plus sign. So this object is perfectly fine because the vertex operator does not have to have square root cuts when it goes around Z. But it turns out in the Ramond sector, if you want to describe the theory, the vertex operators, you need something which gives square root cuts. Now that can be done using something called a spin field. So the spin field will be defined to be, I'm not going to try to define it yet, but it turns out to be a complicated function of size which require Bosonization, and we'll get there, but I don't want to describe it yet. But the vertex operator is more complicated. Furthermore, when you do this integral here over all the surfaces, when you have non-trivial cycles, so for example, if I'm doing this computation at 2 loops, then not only can psi be periodic or antiperiodic when I go around here, you can also get non-trivial periodicities when I go around these cycles, or these. So that corresponds to having different spin structures on the surface. And the amplitude is only the complete amplitude after summing over the spin structure. Now if you're on a genus G surface, you have 2 to the 2G different spin structures. So this is a complicated sum. Now it turns out the cancellations between the bosons and fermions, so as I mentioned at the beginning, this theory, the bosonic string theory, is inconsistent because it has divergences. This theory turns out to be consistent, but it's crucial that you have cancellations between the bosons and fermions. So just the cancellations come if you, for example, computing a loop amplitude. You could have a loop amplitude where the internal states are bosons and another loop amplitude where the internal states are fermions. So these are space-time bosons and space-time fermions. And after summing the two, you get cancellation. So the sum of these, if there's a divergence here, it turns out that the integration of the fermions, if you have space-time supersymmetry, can cancel this divergence. Now this type of sum is precisely the sum that comes after doing the sum over spin structure. So the sum over spin structure essentially does this sum for you. So before doing the sum, this amplitude diverges. And it's crucial to do the sum over spin structures in order to get this cancellation. So for this reason, it's very hard to see the effects of space-time supersymmetry in this version of the superstring. So this version of the superstring is called RNS because of these authors. So it's difficult to see cancellations. Or prove finiteness. So these are necessary to prove that the theory is consistent in this RNS description. So the cause of this, again, is because psi in this case has spin 1/2, and you only get the space-time supersymmetric spectrum, the space-time bosons and fermions, if you include both sectors of the theory. So the space-time supersymmetry is far from manifest in the sense that in one sector you will just get space-time bosons, and in another sector you'll get space-time fermions, and only after summing these do you see the symmetry. So soon after this was developed, so this was developed in the 70s, there were attempts to try to get formulations in which the space-type supersymmetry was easier to see. Okay? So that's the next thing I want to talk about. But any questions? So again, I don't know if this is completely unfamiliar, slightly unfamiliar, but if people don't ask questions, I really don't know. Okay, so the first thing that people realized was, so this theory has this n equals 1 superconformal invariance. And there are ways to gauge fix this n equals 1 superconformal invariance in which you break Lorentz invariance, and you also break the superconformal invariance, but you preserve some simple features of the theory. So this is called light cone gauge. And the idea is you gauge fix one component of x and one component of psi to be 0. So you have these bosonic and fermionic symmetry, world sheet symmetry, and use this superconformal invariance to gauge one of the components of x and one of the components of psi to 0. And another component of x and psi are fixed because of these constraints. So in this light cone gauge, one has xj and psij, where j goes from 1 to 8. So instead of going from 0 to 9. So the action is similar to before, but it just has 8 degrees of freedom instead of 10. And now we can do something interesting. We're going to split x up into a 4 and a 4 bar of SU4. So j is 1 to 4. And we're going to break SO8 down to U4, or let's say SU4. So of course the action is SO8 invariant, but the idea is to break x and of course psi's into 4 complex pairs and use the property that these complex pairs can be bosonized. So I'm going to call, so again, I don't know if bosonization is something familiar to, I'm sure it's familiar to many of you, but maybe not everybody. But the idea is that you can describe a two-dimensional fermion or a complex, a fermion and its complex conjugate in terms of two-dimensional scalar, which is holomorphic on the world sheet. Now, it was realized by Green and Schwartz in the 80s that if I restrict to SO8, there's another way to write the action using SO8 triality. In terms of SO8 vector, x, but instead of using an SO8 vector for psi, I'm going to use an SO8 spinner for psi, for the fermion. So I'm going to call the SO8 spinner theta. So A is 1 to 8. And of course, SO8 has an 8-dimensional representation, which is a vector, which is a chiral spinner, and also which is an anti-chiral spin. So in this description, instead of having xj and psij, we're going to have x J, and theta A. Now it turns out, please.
The J, the capital J, now is an holomorphic index on the space-time, right? But the arguments of these guys may not be holomorphic on the worldsheet, right?
May not be, that's right. In this case, it turns out they are holomorphic because the psi's are d-bar, but that's a coincidence. If I had done what's called type 2 string, I would have a psi and also a psi bar. So there's no relation between the holomorphic on the worldsheet and the holomorphic in space-time. Is there other questions? Okay, so theta, if I split up SO8 down to U4 in this way, I can choose theta to also split up into theta j and theta j bar. And now the idea is that these theta and theta bars will be related to the same bosons as here. So there's actually a field redefinition which relates these light cone descriptions. Now the reason why I'm telling you this is because these thetas, instead of being either periodic or anti-periodic on the worldsheet, like these, you can define them so that they are always periodic on the worldsheet. So these and the way to do that is I'll define the bosonization in a slightly different way. So maybe I'm going to get confused if I write like this. So I apologize for writing this up, but so of course there are 4 of these and 4 of these. And differently from the psi's, which are just written in terms of phi's, these are exponentials of the linear combinations of the same phi's. Now the way I've chosen these exponentials is that I always have 3 minuses and 1 plus sign. But the plus sign, of course, can either be on the first element, the second, the third, or the fourth. So these are the 4 theta j's, and these are the 4 theta j bars written in terms of the same phi's. So this tells me the field redefinition between psi and theta. And using this field redefinition, it's not difficult to show that if the psi's are either periodic or anti-periodic, the thetas will always be periodic. Okay. Now, why is this important? Well, when we do the computation of the scattering amplitude, the idea was now we have a scattering amplitude computation in which there's no more any sum over spin structures. So now, of course, we're supposed to integrate over the x's and thetas instead of the x's and psi's. But the point is here that there's no, all of the sum over spin structures has gone away. And in fact, space-time supersymmetry is just a shift of theta. So if theta, this obviously leaves the worldsheet action invariant. And in fact, these are just half of the supersymmetries. It turns out there are 16 space-time supersymmetries just because, as I just erased, a space-time spinor in 10 dimensions has 16 components, and 8 of them are realized in this way in light cone gate. Okay, so this is something nice, which was done in light cone gauge by Green and Schwartz. So this is but then there's the next question, which is, can we obtain this description from a covariant description? So why do we want to obtain this from a covariant description? Well, the amplitudes that we're going to compute here will only preserve a subset of the full SO10 invariance. So first it got broken into SO8, then it got broken into SU4 times U1. And to reconstruct the fully covariant amplitude is a mess. And in fact, it was only done for up to one loop amplitudes. So if one could get the covariant description, which in light cone gauge, or in a gauge similar to this, reduced to this description here, one would have a hope of reproducing these RNS results, Ramon-Schwartz results, in a way in which space-time supersymmetry was manifest. Okay, so the next ingredient that we're going to discuss now is this twisting. So how is twisting relevant? So this was a review of things that were done in the 70s and 80s. So twisting, again, I don't know if this is familiar to people here or not, can be done if you have not an n equals 1 super-Virasor algebra, but you need an n equals 2 super-Virasor algebra. So this is, of course, an n equals 1 super-Virasor algebra. And if I just replace the m's with j's, so if I go to light cone gauge, and I consider this T and G, I can consider a further breakdown in which I construct, let me write it here. So T is the same as before, but now we're going to break G into two pieces, which are called G equals psi j dx j bar, where now capital J still goes from 1 to 4, and G bar I will call psi j bar dxj. Okay, so once again, this is holomorphic in space-time. This has nothing to do with holomorphicity on the world sheet. All of these generators are holomorphic on the world sheet. Finally, you have a U1 generator, which is just psi j bar. So these four generators, T, this G, and G bar, so no longer this one, forms an n equals 2 super-Virasor algebra. And psi, if I write it like this, in this form with T, is still spin 1/2. But now we can twist by adding the following term to T. So this still forms an n equals 2 algebra, but this turns out to shift the central charge to give you central charge 0. And of course, it shifts G and G bar, so that instead of having spin 3/2, G now has spin 1 and G bar has spin 2. Now, if G has spin 1 and G bar has spin 2, that means psi j has spin 0 and psi j bar has spin 1. So we no longer have spin 1/2 world sheet variables. We now have spin 0 and spin 1 world sheet variables. Now, of course, once we have integer spin, we no longer have to worry about this periodicity or anti-periodicity. Now we can require that the spin 0 variables all are periodic, and also the spin 1. Well, this was done in light cone gauge, and now we can also use this relation of psi and theta to write these variables in terms of psi in terms of theta, if we like. Okay, so what is the relation between psi and theta? Well, it's easy to see just from these formulas I wrote down that psi j is equal to theta j times something I'll call sigma psi j bar, where sigma is just equal to s. So we have defined it minus. So sigma and sigma bar are just constructed out of the same phi's, and it's easy to see that if you just do the algebra, that this is the relation between the psi's and the thetas. So we can easily write g and g bar in terms of the thetas just by using this relation. Okay, so this is an n equals 2 version of the light cone gauge theory. And now the idea is, can we get this light cone gauge theory, which has n equals 2, by gauge fixing some covariant theory? So that's the goal of the rest of the talk, which is, can we get by gauge fixing? So the idea is that now we're going to have a scattering amplitude which is computed. We have an integral just over surfaces without the sum over spin structures. Now, of course, we're going to have to integrate over the x's and thetas. But the idea is that now instead of just having the SO8, G and A, now, of course, we're going to have covariant indices here. So this is going to be, instead of being an integration over 8x, it's going to be integration over 10. And the thetas, instead of integrating over 8 thetas, we're going to need 16. Now this is going to be part of the theory, but in addition there might be some extra variables we need to introduce. And essentially these extra variables that we're going to need to introduce is going to be the new feature. Okay, so that's what we're going to describe now. I should say that Green and Schwartz tried to do it with just these x's and thetas, but it turns out they did not succeed. We need some extra variables. For those who know something about bosonic string theory, they relate to the ghosts. So when I discuss this theory for the bosonic string theory, it turns out one integrates over the x's, but you also get some ghosts coming from gauge fixing the two-dimensional metric. In RNS, you also get two-dimensional ghosts coming from integration over the worldsheet graviton and also worldsheet gravitino. In this case, one also needs ghosts. So in general, in the covariant theory, you can either introduce ghosts or you have to divide by some gauge symmetry. Okay. So this is the subject of the last part of the talk, is finding out what sits here. Okay, and that's going to be related to work that's been done starting 2000 and still work in progress. Okay, so are there any questions before I start?
Just one question. The size you started with, you only had 10 of those.
Yes.
In the covariant theory. Then when you reduce the symmetry to 8, the size of the thetas are just a redefinition.
Yes.
You have 8 of both.
Yes.
But now to describe the covariant theory in terms of the thetas, you're having them to be spinors. And
Yes.
what is that leap? Why do I need the 16 of this if they were just a Hilbert definition of the 10 of those?
Okay. So it might be possible to work with a covariant version of these psi's and x's, but that would lead you back to the RNS formalism. Okay? So the idea is that instead of working with the x's and psi's, we're going to work with the x's and thetas. Why? Because the thetas allowed me to have worldsheet variables which were periodic everywhere on the worldsheet. So we want to covariantize not the psi's, but the thetas. Now the thetas are SO8 spinners. So if we want to covariantize an SO8 spinner, the only thing we can have is an SO10 spinner. So we're stuck with the 16. Okay, other questions? Okay. Okay, so to get started, so I guess I have lots of space. Let's do it here. So obviously, the first thing we're going to have to try to do is to enlarge this SU4, right? So now we're going to start with SO10. And there's an obvious thing you can do, which is break it not to SU4, but to SU5. So that, of course, is going to break x into XA and XA bar, where now A is 1 to 5. So that's the obvious generalization of what was done with a light cone gauge. Now when one breaks x in this way, the theta, of course, is also going to split up. So this, of course, has 16 components. And the way it splits up is it splits up into a 5, a 10, or actually a 10 bar, and a 1, which I'll call theta plus. So this is a 5, a 10 bar, and 1. So this is anti-symmetrized in A bar and B bar. So that's how the 16 components of theta split up. Now, I can see I should have done it over here. So I need more space. Now it's clear this theta A is going to be related to the theta J that I had before. But what about the theta A bar? Where is that going to come from? Well, it turns out that theta alpha in this action, I can, of course, generalize this in a simple way. But I can't. There's no 10-dimensional metric which contracts a theta with an alpha index, a 16-component Weyl spinner with itself. You need to contract it with an anti-Weyl spinner. So the only way to write the covariant version of this is by requiring that half of the thetas come from theta alpha. That will be coming from this theta A. And the other thetas are going to come from the conjugate momentum to theta alpha, which I'll call P, which is going to be an anti-Weyl spinner. So P alpha is going to split up into a 1, 10, and 5 bar, which I'll write with lower indices. So this is going to generate theta A, or the thing I call theta J, and this is going to generate the thing I called PJ, theta J. So this is, of course, a 5 bar, which breaks up into a 4 bar and a 1. So that's the first new ingredient, is that theta has a conjugate momentum which is not the same as theta. And this is, of course, going to be spin 0, because after twisting, this one was spin 0, and this one is going to be spin 1. So this is spin 0 and spin 1. But we're not finished yet, because these degrees of freedom, of course, have many more fermions than bosons, because I've started with 8 bosons and 8 fermions, but now I have 32 fermions and 10 bosons. So you're still missing some bosons. And those are going to come from things which will be interpreted as ghosts. So theta alpha will have some ghost associated with it, which is going to contain these degrees of freedom. And P alpha will also have some bosons associated with it. So now we have 32 fermions from here. We have 10 bosons from here. We're missing 22 bosons. If we want to have an n equals 2, Will-Cheat supersymmetric system, we better have the same number of bosons and fermions. Now, if I just require that lambda alpha only has 11 degrees of freedom instead of 16, I get the right counting. But of course, the way I've described it, this is not the covariant object, because lambda plus and lambda bar AB bar, if you do a Lorentz transformation, they will in general transform into this other components. But if I put a constraint on lambda, which is this constraint here, it turns out that lambda only has 11 independent degrees of freedom. So although lambda has 5 extra components in addition to these 11, the other 5 components are related to these 11, so they're not independent. So this condition here is called the pure spinor condition. So Cartan discussed this in the 30s, and the idea is that there are irreducible representations of SO10, or in general SO2D, which have less independent degrees of freedom than a Weyl spinor. So this is a constrained spinor, which turns out to have 11 complex degrees of freedom. Okay, so one more thing to say about pure spinor, which will become relevant later. It turns out to parameterize this space. So of course, in 2D dimensions, this would be SO2D over UD. Okay. So this has 11 independent complex degrees of freedom. So we have to add to the action these new degrees of freedom. So we have 10 bosons here. We have 32 fermions here. So, and we have 22 bosons here. So the central charge is easy to show. It gives you central charge 0, as you need for a twisted n equals 2 theory. There's one more nice thing you can test, which is that the level of the Lorentz algebra is the same as you have in the RNS formalism. So of course, the Lorentz generators in the RNS formalism are just psi m, psi n. Now, this has level +1 if you look at the SO10 Kac-Moody algebra. In this new description, we have p's and thetas, and each of them has their own Lorentz current. So you have this Lorentz current for the p's and this Lorentz current for the pure spinors. And it turns out, if you compute the SO10 Kac-Moody algebra of this system here, it turns out to give you +4. And if you compute for this system of pure spinors, you get -3. So the sum is still +1. So not only do you get cancellation of the conformal anomaly, also you get the correct level of the Kac-Moody algebra coming from the SO10 current algebra. Okay, so this is the new degrees of freedom that will need to be introduced. And now one still has to construct the n equals 2. So I have to tell you how the n equals 2 generators act on these variables. And essentially one can read this off by requiring that they reproduce the n equals 2 algebra that I discussed earlier in the Light-Cone gauge. So how do the n equals 2 generators act? So I'll write down what T is. So T is obviously just so G is a little bit more complicated. So it will take thetas into lambdas, and it will take x's into these thetas. So what does that mean? So G is going to be of this form. So it's going to take remember before I had dxa bar psi, or dxj bar psi j. In this case, psi j was related to theta j sigma. In this case, this sigma is going to be replaced by lambda plus. And it turns out that sigma bar is going to be replaced by 1 over lambda plus. So what it takes xa into is not psi a, but into this object here. Now, g bar will be similar. So before it was dxj psi j bar. In this case, remember, theta j bar is going to be replaced by p j. So this becomes dxj pj over lambda plus. So that's how the n equals 2 generators act on the x's. But then, of course, you also have these additional degrees of freedom. So that's going to transform the thetas into the lambdas, which will be represented by this term here. And it's going to transform the w's into these p's. So that turns out to be this term. So this is t, g, and g bar. And it turns out that j is, and then there's a, so this is the n equals 2 algebra, which in light cone gauge, so light cone gauge means essentially eliminating the thetas which are not in this theta a and the p's which are not in this pa. So in light cone gauge, this n equals 2 reduces to the light cone that we had before. And it's still not manifestly covariant, but it turns out you can make it covariant. By combining at least the terms in J into something which I'll call lambda alpha d alpha, where d alpha is equal to p. Now it turns out this object here is related to the space-time supersymmetric derivative. So when you quantize, p alpha is the canonical conjugate to theta, and dx is the canonical conjugate to x. So when you act on some operator, or take the singularity of d alpha with some operator, it's the same thing as taking the space-time supersymmetric derivative of that operator. What this means is that if you have a vertex operator and you would like it to satisfy that it's a chiral operator, so g of v equals 0, then it turns out because of the form of g, turns out that this implies that lambda alpha d alpha. So this v I'm defining as a function of just the x's and thetas. And this equation here was first shown by Paul Howe in the 90s to describe super-Yang-Mills. The way it does that is that v of x theta is written in terms of a gauge superfield of super-Yang-Mills. So this is supposed to resemble the formula we had before for the gluon in the original version of the superstring, but it extends it now to a superfield. So A alpha of x theta includes this term, but it also includes the space-time fermion. So this is equal to this term here, but it also has a term of this type, which I called sigma before. So this is the gluon. But if you expand it out in theta and use the relations to this sigma that I defined earlier, this is going to be the vertex operator for the gluing. Okay, so in this description, the vertex operator for the gluon and gluino appear in this very symmetric form. So involving the x and theta, but also involving in a crucial way these extra lambda variables, which I can interpret as ghosts. And finally, now one knows how to formulate the theory here in terms of these extra variables. And one can, in fact, do this computation. And for all computations that were done in the RNS formalism, it was also done here. And you can show that you get the same answer, of course. But this is much more powerful in the sense that in this description, now one has all these fermionic zero modes, which can be used to imply these vanishing theorems that I mentioned at the beginning, coming from supersymmetry. Now, there's still an open question, which is how to prove. So we can check that the amplitudes give the same answer, but we don't have a direct proof that the two formalisms are equivalent. So that's still an unsolved problem. So although we have this nice n equals 2 description of the superstring, we don't have a proof yet that it's equivalent to this RNS description. Okay, so that's something that's still a work in progress, and I'll stop there.